There is a moment, perhaps you have felt it, when you step outside on a clear night, tilt your head upward, and feel the full weight of the sky settle over you. Not with fear, not with urgency, but with something quieter, something older, a feeling that has no precise name in any language, yet every human culture across every era has known it intimately. It is the feeling of smallness, and strangely, comfort. Tonight, we're going to explore something that the most powerful telescope humanity has ever built, the James Webb Space Telescope, has shown us in recent years. Something that has caused scientists, cosmologists, and Nobel Prize-winning physicists to pause, to reconsider, to gently, carefully, and with great scientific precision say the words, "Perhaps we do not fully understand the universe we live in." This is not a frightening statement. It never has been, not truly. Because at every point in human history when our understanding shifted, when the Earth was revealed to orbit the Sun, when galaxies beyond our own were discovered, when light was found to have a speed, that shift did not diminish us. It expanded us. Tonight, we journey to the edge of the observable universe. We will sit quietly with the discoveries that James Webb has placed before us. We will explore what Nobel laureates have said about the nature of our cosmic home, and we will wonder, together gently, what it might mean if the universe is stranger, older, and more layered than even our finest models have predicted. There is nothing to fear in these ideas, only quiet, patient wonder. If you love exploring the cosmos, a like and subscribe would mean the world to us. For most of the 20th century, cosmologists worked from a framework, a model, that described the universe with remarkable elegance. It is called the Lambda CDM model. The name is technical, but the idea is profoundly beautiful in its simplicity. The universe, this model tells us, began approximately 13.8 billion years ago. Not in a particular place, not from a single point sitting within empty space, but rather, space itself began. Time itself began. And from that beginning, which we call the Big Bang, everything expanded outward. In those first moments, matter and energy existed in a state of unimaginable heat and density. Gradually, over hundreds of millions of years, gravity gathered hydrogen and helium into great clouds. Those clouds collapsed under their own weight, and the first stars ignited, ancient, enormous, burning with a brilliance we can barely imagine. Galaxies formed around these stars, clusters of galaxies formed, and the universe continued to expand, not like an explosion outward into pre-existing space, but like the very fabric of space itself stretching in all directions simultaneously. This model, supported by decades of careful observation, by the cosmic microwave background radiation, which is the faint afterglow of the Big Bang still visible today, by the measured distances of galaxies, by the behavior of supernovae across cosmic history. This model became the foundation of modern cosmology. It was, and in many ways remains, one of the greatest intellectual achievements in the history of human inquiry. And yet, the James Webb Space Telescope, peering deeper into the cosmos than any instrument before it, has returned images and data that have made cosmologists do something wonderful and uncomfortable in equal measure. Look again, more carefully, with fresh eyes. Before we explore what James Webb has found, let us take a moment to understand what this instrument is and why its observations carry such extraordinary weight. The James Webb Space Telescope, known simply as Webb, was launched on the 25th of December 2021. It now orbits the Sun approximately 1.5 million kilometers from Earth, positioned at what scientists call the second Lagrange point, a location of gravitational equilibrium where it can remain stable and cool. Webb is not simply a larger version of the Hubble Space Telescope, though it is considerably larger. Its primary mirror spans 6.5 meters across, nearly 3 times the diameter of Hubble's, but the true revolution lies in where Webb looks. While Hubble observed primarily in visible light and ultraviolet wavelengths, Webb is designed to observe in infrared, heat light essentially, light that has been stretched by the expansion of the universe itself. Here is why this matters profoundly. When light travels toward us from an extremely distant galaxy, the expansion of space stretches that light. What began as visible light becomes infrared by the time it reaches our instruments. Only a telescope sensitive to infrared can capture these ancient photons. Only Webb can truly see the earliest epochs of cosmic history. When Webb turns its mirror toward the deep sky, it is not merely looking far away in space, it is looking far back in time. Each photon that lands on Webb's detectors carries information from a moment in the universe's past, some of them from when the universe was only a few 100 million years old. Think of it this way. If the universe's entire history were compressed into a single year, Webb is now showing us photographs from the very first days of January. Before that, we had only glimpses, blurred, distant, uncertain. Now with Webb, the images are sharp, detailed, unexpected, and what they show has prompted some of the most careful and fascinating scientific conversations of our era. Imagine, if you will, building a house. You begin with the foundation, then the frame, then the walls and roof, each stage taking its necessary time. You cannot have the third floor before the first. The sequence is fixed by physics and logic and the patient passage of time. Cosmologists expected the early universe to follow a similar logic. In the aftermath of the Big Bang, matter was distributed almost, but not perfectly, uniformly. Those tiny variations in density seeded the first structures. Gas collapsed into stars. Stars formed clusters. Clusters merged into proto-galaxies. And gradually, over hundreds of millions of years, these proto-galaxies matured into the large, structured, spiral and elliptical galaxies we observe in the nearby universe. The process was expected to be slow, orderly, sequential. When Webb began returning its first deep field images in 2022 and continued through 2023 and 2024, astronomers pointed it toward patches of sky that Hubble had studied, expecting to see a few ancient, small, irregular proto-galaxies in the earliest cosmic epochs. Instead, they found something that prompted one researcher to describe the experience as analogous to finding dinosaur fossils in strata where they simply should not be. They found massive, well-formed, structured galaxies with stellar masses comparable to or exceeding the Milky Way, existing when the universe was only 300 to 600 million years old. Galaxies that, according to our best models of galaxy formation, should not have had enough time to accumulate that much mass, form that many stars, and organize themselves into such coherent structures. The universe, it appeared, had been surprisingly productive in its infancy. Astonishingly, almost impossibly productive. The quiet word that began to circulate among cosmologists was this: tension, not crisis, not catastrophe, but a careful, scientific tension between what the models predicted and what the observations revealed. There is a number at the heart of modern cosmology, a single value that describes something profound, the rate at which the universe is expanding. Astronomers call it the Hubble constant, named after Edwin Hubble, who first observed that distant galaxies are moving away from us. The faster and farther away a galaxy is, the more its light is stretched toward the red end of the spectrum. From this elegant observation, an entire science of cosmic expansion was built. For decades, measuring the Hubble constant precisely was one of the central goals of observational cosmology. The value matters enormously. It tells us how old the universe is, how large the observable universe has become, and critically, how the universe will behave in the far future. Here is where something quietly remarkable has emerged. When cosmologists measure the Hubble constant using the cosmic microwave background, that ancient afterglow of the Big Bang, they obtain one value. When astronomers measure it using objects in the nearby universe, certain types of pulsating stars, certain types of supernovae, they obtain a different value, a measurably, stubbornly, persistently different value. The two measurements do not agree, not by a small margin that might be explained by measurement error, by a margin that has grown as measurements have become more precise, into what physicists describe as a 5 sigma discrepancy. In the language of statistics, 5 sigma means the probability of this disagreement arising by chance is extraordinarily small, less than 1 in 3.5 million. This disagreement has a name now. It is called the Hubble tension, and it is one of the deepest puzzles in contemporary physics. What James Webb has done, with its extraordinary precision, is sharpen this tension further. Rather than resolving it, Webb's measurements of cosmic distance markers have, in many cases, confirmed that the discrepancy is real. It did not go away when we looked more carefully. The universe appears to be expanding faster than our best model of its early history would predict. Somewhere, in the equations that govern cosmic evolution, something may be missing. In 2011, the Nobel Prize in Physics was awarded to 3 astronomers, Saul Perlmutter, Brian Schmidt and Adam Rees, for their discovery that the expansion of the universe is accelerating. Using observations of Type 1a supernovae, which function as reliable cosmic distance markers, like standard candles in the dark, they found that the universe is not merely expanding, but expanding faster and faster over time. This discovery introduced into our cosmological vocabulary a new term, dark energy, a mysterious component of the universe, invisible, detectable only through its effects, that appears to be pushing space apart, counteracting gravity on the larger scales, driving the accelerating expansion. Dark energy, in our current best model, constitutes approximately 68% of the total energy content of the universe. We have no idea what it is. Adam Rees, one of those Nobel laureates, has been among the most careful and persistent voices studying the Hubble tension. When Webb's measurements refined the distances to the standard candles his team uses, rather than finding resolution, the tension deepened. In careful scientific language, Rees and his colleagues have noted that the discrepancy demands explanation, that it is no longer comfortable to attribute it to systematic measurement error. There is something, the data suggests, that our standard model does not capture. The phrase you may have encountered, that something is wrong with our universe, is perhaps dramatized in its popular expression. Scientists rarely use the word wrong. They use words like incomplete, intention, requiring extension. But the underlying meaning carries genuine weight. The universe that Webb is revealing may require additions to our model, modifications, new physics, and that prospect, the prospect of new physics, is one of the most thrilling and calming ideas in all of science. It means there is more to learn. The universe has not finished surprising us. Let us step back for a moment and consider the full inventory of the universe as we currently understand it. Ordinary matter, everything made of atoms, everything that forms stars and planets and dust and gas and living creatures, and the device through which you are hearing these words, constitutes approximately 5% of the total energy content of the universe. 5%. The remaining 95% is composed of things we have inferred but never directly detected. Dark matter, approximately 27%, is a form of matter that does not interact with light. It does not emit, absorb, or reflect electromagnetic radiation of any kind. It is invisible to every telescope we have ever built. We know it exists because of its gravitational effects. Galaxies rotate in ways that only make sense if surrounded by enormous halos of invisible mass. Clusters of galaxies bend light from objects behind them, a phenomenon called gravitational lensing, in ways that require far more mass than their visible stars and gas can account for. Dark matter is the invisible scaffolding upon which the visible universe is draped. Without it, galaxies would not have formed. Cosmic structure would not exist in the form we observe it. In a very real sense, dark matter is the architecture of everything, and yet, we have never seen it, never touched it, never captured a single particle of it in a laboratory. Dark energy occupies the remaining 68%, as we noted, equally mysterious, equally inferred, equally essential to our model. What James Webb observes, in a sense, are the visible consequences of these invisible dominators. The early galaxies that formed too quickly may have done so because dark matter halos were denser in the early universe than predicted. The expansion that accelerates may trace the behavior of dark energy across cosmic time, in ways our simplest models do not capture. The universe, in its vast majority, remains invisible to us. And yet, here we are, tiny, ephemeral. We are carbon-based observers, mapping the invisible from our small blue world. There is something deeply beautiful in that asymmetry. Approximately 380,000 years after the Big Bang, something happened that cosmologists describe as one of the most significant events in the history of the universe. For the first time, the universe became transparent. Before that moment, the cosmos was a plasma, a hot, dense fog of protons and electrons so energetic that photons of light could not travel freely. They would scatter almost immediately, trapped in a brilliant but opaque sea of charged particles. The universe glowed, but nothing could see through it. Then, as the universe cooled to approximately 3000 degrees Kelvin, electrons and protons combined for the first time into neutral hydrogen atoms. The fog lifted. Photons, suddenly free, streamed outward in all directions. That light, released in a single cosmic moment of transparency, has been travelling ever since. Today, after 13.8 billion years of travel through an expanding universe, that ancient light has been stretched to microwave wavelengths. It arrives at our detectors from every direction in the sky simultaneously. A faint, almost perfectly uniform glow, the cosmic microwave background. The CMB is, in a very real sense, a photograph of the infant universe. The tiny variations in its temperature, fluctuations of only 100,000th of a degree, represent the seeds of all structure that would later form. Those minute wrinkles in the baby universe grew over billions of years into galaxy clusters, cosmic filaments, and the vast voids of the cosmic web. When cosmologists measure the Hubble constant from the CMB, they are extrapolating from this ancient snapshot, using our best model of how the universe evolved from that moment to the present. The value they extract assumes the model is complete, correct. But if the universe evolved differently than the model predicts, if there was something unusual in those first moments, some additional component, some different behavior of dark energy or dark matter in the early cosmos, then the extrapolated value might genuinely differ from what we observe today. This is why the Hubble tension is so profound. It may be pointing to a gap in our story of the universe's first moments, a chapter, perhaps, that we have not yet written. Among the things Webb has illuminated most vividly is the era of the first stars, what astronomers poetically call cosmic dawn. In the darkness following the CMB's release, the universe entered what is called the cosmic dark ages. There were no stars, no galaxies, no light, save the fading afterglow of the CMB itself. The universe was cold, dark, and composed almost entirely of hydrogen and helium gas, drifting slowly under gravity's patient pull. Then, after perhaps 100 to 200 million years, something ignited. In the densest pockets of dark matter halos, where gravity had quietly concentrated gas over millions of years, the first stars switched on. These were not stars like our Sun. They were giants, perhaps hundreds of times more massive, burning with a ferocity our Sun cannot approach, and blazing blue-white against the cosmic darkness. They lived brief, violent lives, millions of years, not billions, and died in spectacular supernova explosions. Those explosions seeded the universe with something precious. The first stars were composed almost entirely of hydrogen and helium, but inside their cores fusion had built heavier elements: carbon, oxygen, silicon, iron. When those stars exploded, they scattered these heavy elements into the surrounding gas. Those elements, forged in stellar cores and dispersed by stellar death, became the building material for the next generation of stars, and the next, and eventually for planets, and for life. Every carbon atom in your body was forged inside a star that died long before our Sun was born. Every oxygen molecule in the air that moves gently through your lungs traces its origin to those ancient stellar furnaces. We are not separate from the cosmos. We are made of it. We are, in the most literal and physical sense, the universe knowing itself. Webb has now observed galaxies from this era, galaxy candidates from when the universe was only a few 100 million years old. And what it sees suggests that even then, the universe was building structures more quickly, more efficiently than we expected. Let us return to those early unexpected galaxies, the ones that have prompted so much careful reconsideration. In 2022 and 2023, Webb identified several galaxy candidates existing at what astronomers call high redshift, meaning the universe, at the time their light was emitted, was only a fraction of its current size. And some of these galaxies appear to date from when the universe was only 300 million years old. Others, in subsequent analyses, have been tentatively placed even earlier, within the first 200 million years. What is striking is not merely their age, but their character. These are not the small, irregular, fragile protostructures theorists predicted for such early epochs. Some appear massive. Some appear to have already formed large numbers of stars, stellar populations comparable in richness to galaxies we see nearby, galaxies that have had billions of years to build themselves. One galaxy candidate, studied extensively in Webb's early deep field observations and referred to in scientific literature as a candidate bright galaxy from the first few 100 million years, Rho appeared to contain a stellar mass that would require our models of galaxy formation to work at extraordinary efficiency, converting gas to stars at rates that push against the upper limits of what physics should allow. Astronomers have a term for this. They call it the impossibly early galaxy problem, though the word impossible is always used in the context of our current model, not as a statement of absolute impossibility. Models can be revised, models can be extended. Several explanations have been offered with measured scientific care. Perhaps dark matter behaved differently in the early universe, clumping more rapidly, providing denser halos for galaxy formation to accelerate within. Perhaps the first stars were more efficient than we assume. Perhaps the way we define and measure the stellar mass of distant galaxies introduces systematic uncertainties that make things look more extreme than they are. Or perhaps, and this is the possibility that many cosmologists are holding open with quiet intellectual honesty, our understanding of the very early universe is incomplete in ways we have not yet identified. Zoom out, far out, beyond individual galaxies, beyond galaxy clusters, until the individual lights of a trillion stars blur into something else entirely. At the very largest scales, hundreds of millions of light years and beyond, the universe is not random. It is structured, organized into what astronomers call the cosmic web, a vast network of filaments, sheets, and nodes, separated by enormous empty voids. Imagine, if you will, the most elaborate spider's web ever constructed. Now expand it to fill the observable universe. The threads of this web are filaments of dark matter and gas along which galaxies cluster. Where filaments intersect, galaxy clusters form, the most massive gravitationally bound structures in the universe. Between the filaments lie the voids, regions of space that can stretch 300 million light-years or more across, containing almost nothing. Faint, ghostly, nearly empty. Our own Milky Way galaxy is part of this web. We exist within a structure called the local group, a modest collection of galaxies dominated by the Milky Way and our neighbour Andromeda. The local group is, in turn, part of the Virgo supercluster, which is itself part of an even larger structure called Laniakea, a supercluster spanning 500 million light-years and containing the mass of 100 million billion suns. And Laniakea, immense as it is merely one region of the cosmic web. This structure, these filaments and voids, formed from those tiny temperature fluctuations in the early CMB. Gravity amplified those seeds over billions of years, drawing matter along the filaments and emptying the voids, weaving the architecture we observe today. Webb has begun to probe whether the large-scale structure of the early universe matches our predictions, and in some regions the clustering of the early galaxies appears, again, more advanced than models suggest, as if the cosmic web was weaving itself together more efficiently than expected. Among the most profound and elegant ideas in modern cosmology is the theory of cosmic inflation. It addresses a question that the simple Big Bang model cannot answer on its own. Why is the universe so smooth? If you measure the temperature of the cosmic microwave background in opposite directions of the sky, regions so far apart that, in a straightforward Big Bang model, they could never have been in contact with each other, could never have exchanged energy. You find that their temperatures are identical to extraordinary precision. This is called the horizon problem. How can regions that never communicated be at the same temperature? The answer offered by inflation theory is both radical and elegant. In the very first fraction of a second after the Big Bang, within the first 10 to the power of negative 32 seconds, a span of time so brief it has no analogy in human experience, the universe underwent a period of exponential expansion. Space doubled, and doubled again, and again, at a rate that vastly exceeded the speed of light. This is not a violation of relativity. No object moved faster than light. Space itself expanded. The fabric of space-time stretched. In this fleeting moment, a region that was once in thermal equilibrium, that had been in contact, that shared the same temperature, was stretched to encompass the entire observable universe. That is why the CMB is so uniform. Every part of our observable universe descends from a single tiny region that was, once, in contact with every other part. Inflation also stretched quantum fluctuations, microscopic variations in energy at the quantum scale, to macroscopic size, exceeding the very temperature variations in the CMB that would eventually grow into galaxies and stars and planets, and the light of consciousness looking up at the night sky and wondering. We have never directly confirmed inflation, but its predictions match observation with extraordinary accuracy. It remains one of the most successful theoretical frameworks in cosmology, and yet, different models of inflation make different predictions. Webb's observations of the early universe provide new tests of inflationary models. Some versions of inflation predict specific patterns of galaxy distribution, specific rates of structure formation. If the early galaxies Webb finds continue to contradict the simplest models, inflation theorists may need to revisit their parameters. The first moment of the universe remains, in many ways, its deepest mystery. One of the most striking features of Webb's early universe observations involves black holes. Supermassive black holes, objects containing millions or billions of times the mass of our Sun, sit at the centres of most large galaxies in the nearby universe, including our own Milky Way. Our central black hole, called Sagittarius, a star, contains approximately 4 million solar masses. These objects grow through two mechanisms: by consuming surrounding gas and dust, and by merging with other black holes when galaxies collide. Both processes take time, considerable time. When astronomers discovered, in the late 20th and early 21st centuries, that supermassive black holes existed in the early universe, when the cosmos was only 1 billion or so years old, it raised questions. How did they grow so large so quickly? What were their seeds? Webb has now found evidence of actively feeding black holes, known as quasars, in galaxies that existed when the universe was less than 1 billion years old. Some of these black holes appear to already contain hundreds of millions of solar masses. A few candidates may be even more massive. The formation of these objects in such a short cosmic time presents what theorists call the seed problem. If black holes began as the remnants of the first massive stars, with masses perhaps a few hundred times that of the Sun, they would need to grow at the maximum theoretical rate, called the Eddington limit, almost continuously for hundreds of millions of years to reach observed sizes. This is possible, but extremely unlikely for so many of them. Alternative theories propose that the first black holes formed directly from the collapse of massive gas clouds in the early universe, without passing through a stellar phase, creating what are called direct collapse black holes, with initial masses of perhaps 100,000 solar masses. These seeds would grow to supermassive scales more readily. Webb has found candidate objects that may be consistent with this direct collapse pathway. The investigation is ongoing, careful, and deeply fascinating. The universe, it seems, was building its most extreme objects with remarkable speed. Let us address directly the remarkable statement that has circulated, the suggestion from respected scientists that what we observe may not fit the universe we thought we inhabited. Let us approach it with the same care and precision that the scientists themselves employ. When a physicist or cosmologist says, in essence, that something fundamental may need revision, that the universe is behaving in ways our current model does not fully predict, they are not saying the universe is broken. They are not saying science has failed. They are saying something far more hopeful. They are saying, we have learned enough to know the edges of our knowledge. We have instruments precise enough to detect the places where our maps do not match the territory. And that detection, that awareness of the gap, is itself a form of profound progress. The lambda CDM model, the standard cosmological model, is not wrong in the way that a broken clock is wrong. It describes an enormous range of observations with extraordinary accuracy, and the CMB matches its predictions beautifully. The large-scale structure of the universe in broad strokes matches its predictions. The existence and abundance of light elements formed in the first few minutes after the Big Bang matches its predictions. What Webb is revealing are tensions, discrepancies at the edges. The early galaxies are too massive, too numerous, too organized. The Hubble constant measured locally disagrees with the value inferred from the early universe. The supermassive black holes arrived too soon. Each of these tensions, on its own, might have an explanation within our current model. Taken together, with the accumulating weight of high-precision Webb data, they form a pattern that thoughtful scientists are taking seriously. The universe is not wrong. Our model of it, our necessarily incomplete human model, may need expansion. And history tells us with quiet certainty that when cosmological models expand, the resulting science is always more beautiful than what came before. When the standard model of cosmology shows signs of tension, theorists begin to explore. This is the natural, healthy rhythm of scientific progress. Some of the directions being explored are worth considering briefly, not as settled conclusions, but as the live, breathing edge of human inquiry. One area of active exploration involves modifying our understanding of dark energy. In the simplest version of our model, dark energy is a cosmological constant, a fixed energy density inherent to empty space itself, unchanging across all of time. But it is possible that dark energy is not constant. Some models propose that it varies over cosmic time, stronger or weaker in different epochs. This variation could affect the expansion rate in ways that account for the Hubble tension. Recent data from the Dark Energy Spectroscopic Instrument, DESI, a ground-based survey mapping the three-dimensional distribution of galaxies, released in 2024 results suggesting that dark energy may indeed have varied over time. This is a tentative result, requiring confirmation. But it aligns with theoretical work that had long proposed dynamic dark energy as a resolution to cosmological tensions. Another direction involves the possibility of new, relativistic species, particles or energy forms that existed in the early universe but have since diluted away. Then adding such components could shift the predicted Hubble constant from the CMB toward the locally measured value. A more radical proposal, sometimes called early dark energy, suggests that a brief episode of additional dark energy existed in the early universe just before the CMB epoch, boosting expansion slightly and altering the scale of cosmic structures. This would shift the CMB-derived Hubble constant upward, toward the locally measured value. None of these proposals has been confirmed. All are under active investigation. The field is alive with careful, rigorous, genuinely open inquiry, the kind of scientific atmosphere that tends to precede major discoveries. It is worth pausing to appreciate this moment. We are living in the era when humanity's instruments have become sensitive enough to detect the incompleteness of our deepest cosmological models. That is a remarkable place to be. James Webb continues to observe. As of the writing of this script, it has completed several years of scientific operations, and its archive of data continues to yield discoveries. Its mission is expected to continue for at least another decade, potentially longer. Among its ongoing priorities are the further characterization of those early, massive galaxies, obtaining spectroscopic measurements that confirm their distances and allow analysis of their stellar populations and chemical compositions. Spectroscopy, which spreads starlight into its component wavelengths like a prism spreading sunlight into a rainbow, reveals the fingerprints of specific chemical elements. It can tell us the ages of stars, the abundance of heavy elements, the presence of an active black hole. For the early universe galaxies, spectroscopy is crucial. Some of the most extreme objects detected in Webb's imaging, the ones that most challenge our models, require spectroscopic confirmation to rule out the possibility that they are simply unusual nearby objects, misidentified as distant ones. Webb is also studying the circumgalactic medium, the diffuse gas that surrounds galaxies, in the early universe. This reservoir of gas feeds star formation, and understanding how it behaves in early cosmic history helps constrain models of galaxy evolution. Beyond cosmology, Webb has revealed extraordinary details of planet-forming disks around nearby young stars, detected atmospheric components of exoplanets, and studied the chemistry of nebulae within our own galaxy with unprecedented clarity. It is an instrument of extraordinary generosity. Every observation it makes adds to a picture of the cosmos that humanity has been building for centuries, one measurement, one photon, one careful inference at a time. The universe is patient with our questions. Webb helps us ask better ones. Let us take a moment, a long quiet moment to simply contemplate scale. The observable universe, the region of space from which light has had time to reach us in the age of the universe, extends approximately 46 billion light-years in every direction. This is larger than the 13.8 billion light-year figure for the age of the universe, because space itself has been expanding while that light travelled toward us. 46 billion light-years in every direction. A sphere of that radius centred on our position. Within that sphere, there are an estimated 2 trillion galaxies. 2 trillion. Each galaxy containing anywhere from a few hundred million to a few trillion stars. Our own Milky Way holds somewhere between 200 and 400 billion stars. The number of stars in the observable universe is estimated at approximately 10 to the power of 24. That is a 1 followed by 24 zeros. There is a well-known observation that this number exceeds the count of grains of sand on all of Earth's beaches. In fact, it exceeds the count of atoms in a grain of sand. The comparison strains language and imagination equally. Yet here, in this vast expanse, on a small rocky planet orbiting an unremarkable yellow star in the outer arm of one average spiral galaxy, among 2 trillion, here consciousness arose. Here something looked up and asked, "What is all of this?" The philosopher in us wants to find meaning in that improbability. The scientist in us notes that in a universe of 2 trillion galaxies, even rare events can occur in many places. Both responses are honest. Both are incomplete. The truth likely encompasses something neither discipline has yet fully articulated. Webb observes this universe from our small vantage point and sends back evidence that even the known portion, the 46 billion light-year sphere we call observable, is stranger and richer than we imagined. Beyond the observable horizon, the universe almost certainly continues. Potentially forever. We cannot see it. We cannot reach it. Its light has not had time to find us. The universe is larger than the part of it we can know. This is not a source of anxiety. It is, if anything, a source of profound humility. And humility, genuine, earned humility, is perhaps the most honest relationship we can have with something as vast as existence. Consider time. Not the time that moves through your evening or your year or even a human lifetime. Consider time at the scale the universe requires. The universe is approximately 13.8 billion years old. Our Sun is approximately 4.6 billion years old, 1/3 the age of the universe when it formed. Life on Earth appears to have begun approximately 3.5 to 4 billion years ago. Anatomically modern humans have existed for perhaps 300,000 years. In cosmic terms, we are extraordinarily new. Now consider the future. Our Sun will continue to shine for approximately another 5 billion years. The Milky Way and Andromeda galaxies will collide in approximately 4 to 5 billion years. A collision so slow and spacious, given the vast distances between stars, that our solar system is more likely to be flung to a new orbit than to suffer any direct stellar collision. Stars like our Sun will continue forming in the universe for roughly 1 to 2 trillion years, 100 times longer than the current age of the universe. After that, star formation will slow and eventually cease as galaxies exhaust their gas supplies. The last stars, tiny, dim, red dwarfs, may shine for 10 trillion years or more. 10 trillion. After the last stars fade, what remains will be black holes, neutron stars, white dwarfs, and cold stellar remnants drifting silently through an ever-expanding and cooling universe. Over timescales that make the current age of the cosmos seem like a single heartbeat, even protons, if they are not perfectly stable, as some theories suggest, may decay. Black holes, through a quantum process called Hawking radiation, may slowly evaporate. The very far future of the universe is a subject of legitimate scientific inquiry, and its contemplation is not unsettling so much as humbling. We exist in what is, cosmically speaking, the bright early morning of a universe that has an almost incomprehensibly long story ahead of it. We are early, we are fortunate, we are paying attention at the right moment. It is worth pausing, as we draw toward the later portions of our journey tonight, to reflect on the nature of science itself, particularly as it relates to moments like this one, when observations strain our models and understanding must expand. Science is sometimes presented in popular accounts as a collection of settled facts, a compendium of confirmed knowledge static and complete. But this is not science. Science is a process, a living, self-correcting, continuously deepening conversation with the universe. When James Webb reveals galaxies that our models did not predict, scientists do not panic. They do not abandon the framework that has served so well. They examine the new data carefully. They consider systematic errors, ways in which the measurement itself might introduce biases. They propose modified models and test them against all available data, not just the anomalous observations. They publish, debate, refine. This process is slow. It is deliberate. It operates on timescales of years and decades, not news cycles. A single unexpected observation does not overturn a model. A pattern of unexpected observations, confirmed by multiple independent methods, begins to demand explanation. We are, with the early Webb results, somewhere in the middle of this process. The anomalous early galaxies have been identified. Some have been spectroscopically confirmed. The Hubble tension has been measured with increasing precision. Alternative models are being constructed and tested. The outcome? What our cosmological picture will look like in 20 or 30 years, incorporating all of Webb's data, is not yet known. And that uncertainty is not a failure of science. It is science doing exactly what science does, reaching carefully into the unknown with its instruments and its mathematics, and asking with genuine openness what is really there. There is something deeply reassuring about this. The universe is not something that humanity has already understood, packaged, and placed on a shelf. It is a question that every generation inherits, explores more deeply, and passes on, enlarged, to the next. Behind every discovery that James Webb has made are people, thousands of them, engineers who spent decades designing and building an instrument that had to fold origami-like into a rocket, then unfurl perfectly in the cold of space 1.5 million kilometers from Earth. Scientists who proposed observation programs, who competed for telescope time, who waited years for data. Graduate students who processed images at odd hours. Researchers who sat with anomalous measurements and asked carefully whether they were seeing something real. The James Webb Space Telescope was conceived in the 1990s. Its development spanned nearly 3 decades and involved contributions from NASA, the European Space Agency, and the Canadian Space Agency, an international collaboration of extraordinary scope. Its cost, approximately $10 billion, reflects not merely the hardware but the accumulated expertise, the trial and error, the solved engineering problems and discarded solutions of thousands of dedicated careers. When it launched on Christmas Day in 2021, and when it successfully unfolded its golden mirror and reached its final orbit, and when its first images arrived, crisp, deep, saturated with ancient light, the people who had devoted their professional lives to its creation wept. Not from sentimentality alone, but from the accumulated weight of decades of careful, faithful work arriving at its purpose. Those images, those photons that had travelled billions of years to land on a detector, designed and built by human hands, they represent something extraordinary about our species. We are small, we are brief, we are deeply limited in so many ways, and yet we built Webb. We reached with mirrors and mathematics to the edge of the observable universe. We ask questions about the first moments of time. Whatever the universe turns out to be, however the tensions resolve, however the model expands, that act of asking remains one of the most profound things we do. There is a boundary, not a wall, not a barrier, but a horizon, beyond which the observable universe ends. It is called the cosmological horizon, or sometimes the particle horizon. Beyond it, light has simply not had time to reach us. The universe may have existed and evolved in those regions for 13.8 billion years, but the information of its existence travels at the speed of light, and it has not yet arrived. This is not a limit of our instruments. Webb, magnificent as it is, cannot see beyond this horizon. Yet no instrument ever built or conceivable within our current understanding of physics could. It is a fundamental limit imposed by the relationship between the speed of light and the age of the universe, and yet the universe almost certainly continues beyond that horizon. Most inflationary models predict that the universe is vastly larger than the observable portion. perhaps infinitely larger. The patch of universe we can see may be an extraordinarily small fraction of what exists, a bubble of knowable space adrift in an immensity that dwarfs it beyond any meaningful comparison. Some models go further still. The theory of eternal inflation, an extension of the inflationary framework, proposes that inflation continues forever in most of space, occasionally stopping in localized regions that then evolve as individual universes. In this picture, our observable universe, and the vast unobservable expanse that surrounds it, is itself just one bubble among an infinite number, a multiverse of separate, causally disconnected cosmic regions, each potentially with its own physical constants, its own particle physics, its own fate. This is speculative. It may be untestable in any practical sense, but it is a mathematically consistent consequence of inflationary theory, taken seriously by serious physicists. If it is true, then our universe, meaning everything that Webb can see, everything humans can ever in principle observe, is a single note in an infinite symphony of existence. The implications for questions of meaning, uniqueness, and human significance are profound and genuinely open. We sit tonight in a small room on a small planet, contemplating a possibility so large that it contains no adequate words. This, perhaps, is the most honest position available to us, aware of the vastness, at peace with the limits, grateful for the view. We have spent our journey tonight moving outward, from our planet to our galaxy, from our galaxy to the cosmic web, from the early universe to its possible futures, from the observable to the unobservable. Let us for a moment move inward. Consider that the universe, for most of its history, was not observed. Matter existed. Stars burned. Galaxies collided. Black holes consumed. All of this happened in perfect, impersonal silence. No awareness, no witness, no mind to register it. Then, on at least one small world, chemistry became biology, became nervous systems, became awareness. Something in the universe woke up to itself. The universe began, in a limited and local sense, to know that it exists. This is not a poetic metaphor. It is a physical fact. The atoms of consciousness, carbon, hydrogen, oxygen, nitrogen, are the same atoms forged in stellar cores. The neurons that carry the thought I am are made of star stuff. The subjective experience of being, whatever that ultimately is, arose from a universe that was, for most of its history, without it. Whether this is unique to Earth is unknown. The universe is large enough and chemistry rich enough that most scientists consider it unlikely that we are alone. But we have not confirmed the presence of other minds. We remain, for now, the only known place in the cosmos where the cosmos has learned to look at itself, Webb. When it searches the atmospheres of exoplanets for biosignatures, chemical signs of life, is, in a sense, the universe trying to find out whether it has woken up anywhere else. It is consciousness reaching outward to ask whether it is singular or multiple. It is the most profound question an instrument has ever been asked to help answer. We do not yet have that answer. The search is early, and the tools, though extraordinary, are still developing for this particular purpose. But the question itself, the fact that we are asking it, seems like one of the most remarkable things in the universe, perhaps in any universe. As we begin to draw our journey to a close, there is something important to hold, something that the tensions and uncertainties we have discussed tonight offer if we receive them in the right spirit. Incompleteness is not failure. In a universe that has been expanding and evolving for nearly 14 billion years, in a cosmos of 2 trillion galaxies, dark matter halos, ancient light, and quantum origins, the fact that our models are incomplete is not a sign of scientific inadequacy. It is a sign of how honestly science is practiced. It is a sign that we are asking questions at the genuine frontier of knowledge, not in comfortable territory where every answer is already known. The Hubble tension exists because we measure the universe carefully enough to detect it. The early galaxy problem exists because Webb sees deeply enough to reveal it. The mystery of dark energy and dark matter persists because we are honest enough not to pretend we understand what we cannot yet explain. Every generation of cosmologists has inherited puzzles from the generation before. Every generation has resolved some puzzles and uncovered new ones, deeper and richer than the ones before, there is no reason to suppose this pattern will not continue. There is every reason to trust that the physics of the next century will be more beautiful, more accurate and more complete than the physics of today, and we, those of us alive in this early era of Webb observations, in this moment when the Hubble tension is sharpening and early galaxies are confounding our expectations, we are present for the puzzle forming. We are witnesses to the questions being asked. That is a privilege. Quiet, profound, and easy to overlook in the busyness of daily life, but genuinely extraordinary when considered clearly. We are here. We are aware. The universe is showing us its mysteries, and we are listening. There is a quality to the images that James Webb returns that is worth contemplating in its own right. When you look at a Webb-deep field, a long exposure of a small patch of sky, revealing thousands of galaxies at various distances and epochs, there is something that resists immediate comprehension. Each smudge of light is a galaxy. Each galaxy is 100 billion stars or more. Each star may be orbited by planets. Each planet exists in a universe that has been unfolding for nearly 14 billion years. And the image itself, that single frame, required the light from those galaxies hundreds of millions or billions of years to arrive at a golden mirror assembled by human hands. There are no words adequate to this. No scale comparison fully captures it. Numbers help. But only so far. At some point, the mind relaxes its grip on comprehension and moves into something simpler and more honest. Awe. That is not an unscientific response. Awe is, in many ways, the appropriate emotional state for someone genuinely contemplating the scale and age and complexity of the universe. It does not require abandoning reason. It does not require mysticism. It requires only honesty about what the numbers mean when you sit with them quietly. Webb's images are, among many other things, invitations to this kind of honesty. They ask us to look carefully at how large the universe is, how old it is, how strange and structured and filled with things we did not expect. And then to sit with that, not anxiously, not urgently, but with the quiet that scale genuinely demands. In that sitting, something softens. The concerns that fill an ordinary day, the ones that feel enormous at noon and manageable by midnight, find their natural proportion against a backdrop of 2 trillion galaxies, not dismissed, not invalidated, but placed gently in their true context. We are small, and we are precious. And both of those things are true at once. We have travelled far tonight. Not in space, though we have moved through billions of light years of cosmic history, but inward, into the nature of what we know and how we know it, into the edge of the map where the careful drawings of cosmology trail off into the unexplored. James Webb continues to orbit in the cold of space, its golden mirror cooled to approximately minus 233 degrees Celsius, sensitive enough to detect the heat of a bumblebee at the distance of the moon. Night after night, or rather, in the timeless dark of space beyond Earth's shadow, it gathers photons, ancient light. Each photon a messenger from a time before our planet existed. The scientists who analyze that data are asking questions that previous generations could not have imagined asking. They are holding open the possibility that the universe is older than our clocks suggest, or that dark energy is more dynamic than our simplest models allow, or that the very first moments of time were stranger than inflation in its basic form predicts. These are honest, open, patient questions. They are not sources of fear. They are expressions of humanity's most enduring and admirable quality, the refusal to stop asking. Somewhere tonight in a university or a research institute, a graduate student is running a simulation that extends our model of galaxy formation, testing whether a small modification to dark matter's behavior in the early universe might explain the objects Webb has revealed. Somewhere, a theorist is writing equations that describe a dynamic dark energy, checking whether the numbers align with the Hubble tension. Somewhere, an observer is waiting for a spectroscopic result, a pattern of absorption lines in the light of a distant galaxy that may confirm or refute a hypothesis formed from Webb's imaging data. The work continues, quietly, carefully, persistently. And the universe, vast, ancient, composed almost entirely of things we cannot see, continues to expand. galaxies drift apart on the stretching fabric of space-time. Stars are born in clouds of gas and die in brilliance. Black holes accumulate mass at the centres of galaxies. The cosmic microwave background, that ancient glow from the first 380,000 years, continues to redden and cool as space expands, thinning toward invisibility across timescales too long for imagination. In all of that, in the 2 trillion galaxies and the dark matter halos and the cosmic filaments, and the supermassive black holes and the early galaxies that form too quickly, and the expansion rate that doesn't quite add up, we exist. Briefly, improbably, consciously. There is a phrase sometimes used in scientific circles. The universe is not only stranger than we suppose, but stranger than we can suppose. It is attributed loosely to the biologist J.B.S. Haldane, though its sentiment has been echoed by physicists and philosophers ever since. Webb's observations give it a kind of lived reality. The universe is genuinely more intricate and surprising than our models predicted. It is showing us its complexity through the patient work of thousands of scientists and the light of 1 trillion ancient suns. What does this tell us about existence, about our place in it? These are questions that science illuminates but does not fully answer, and perhaps rightly so. They are the questions that each mind, in its quiet moments, must hold and tend in its own way. Tonight, we have held them together. We have stood, metaphorically, at the edge of what is known and looked outward at what remains mysterious. We have considered the scales that dwarf anything human, and also the remarkable fact that anything human exists at all to do the considering. If there is a single thought to carry into the night, it might be this: the universe is not finished with its story. The model that describes it is not finished being written. The telescope that studies it is not finished gathering light, and the mind that wonders about it, your mind in this quiet moment, is participating in something genuinely continuous with all of that. The asking is part of the story. The wondering is part of the universe knowing itself. So let the questions rest now. Let them drift, unresolved, into the soft dark at the edges of sleep. The universe will be there in the morning, still expanding, still ancient, still full of mysteries that patient human curiosity will, one day, partially illuminate. The stars continue to burn, distant and unhurried. The light continues to travel, and somewhere, a golden mirror waits in the cold of space, ready to catch whatever comes next. Thank you for exploring with us tonight. Rest gently in the knowledge that you are part of something vast and old, and, in ways science is only beginning to understand, something that chose, in at least one small corner of itself, to become aware.